Shown in the figure below are two concentric spheres of charge. A charge plus q is uniformly distributed over the outer sphere between radius of r equals b and r equals c. A charge minus q is uniformly distributed over the inner sphere, r less than a. The space between the spheres is empty. Use Gauss' law to find the electric field in all of the four regions. The table to the right of the figure shows a listing of the difficulty level of each one of the parts of this problem. Regions 1 and 3 are easy or very easy. Regions 2 and 4 require a little bit more effort. As you've no doubt picked up by now, the two critical steps in any Gauss law problem are to identify the area of the appropriate surface and to identify the charge enclosed. Typically, a Gauss law problem that is challenging is not challenging because of finding the area, it is instead challenging because of finding the charge enclosed. The shape of the Gaussian surface follows the symmetry of the system. We've got spheres inside of spheres. What shape do you think we're going to get for the Gaussian surface? Answer, we're going to get spheres. The area of the spheres are going to be 4 pi r squared, and that's going to apply to parts 1, 2, 3, and 4. The challenging part in each case is going to be finding the charge enclosed. This is what makes parts 1 and 3 easiest, because since each of these calculations is in a free space area, the charge enclosed is simply a number rather than a calculation based upon a density times a volume, a sigma times an area, or a lambda times an L. Let's quickly review the solutions to 1 and 3 and then move on to the more challenging parts for 2 and 4. When we're in region 1, we will decide that the point P located here, a distance r from the center of the sphere, has a series of points that have the same value of the electric field, and those collection of points are shown as the green dashed sphere. Because we have chosen the surface which has the appropriate symmetry for analyzing our Gauss problem, the normal complicated Gauss law formula is going to simplify into E times A is Q in over epsilon naught, our normal consequence when approaching a Gauss law problem correctly. We then have two items that we need to take care of. As mentioned, every part in this problem is going to use the same area. The surface area of a sphere is 4 pi times its radius squared. However, in this case, we're going to need to consider what's the Q in. And the Q in is actually 0. The reason is that you contain all of the red charge for a total of minus Q, as well as all of the blue charge for another plus Q. Plus Q added to minus Q gives us 0. For that reason, we're able to very quickly write down the answer in region 1 to get the electric field of 0. We can perform a similarly easy calculation for region 3. In region 3, we place our Gaussian surface as shown by the purple dashed lines. We are doing so a radius r away from the center of the sphere. Doing so yields the familiar area term, as well as a simple but not entirely trivial value for Q in. For the purple surface, since we have contained all of the charge in the red ball and none of the charge in the blue ball, our Q in is simply negative Q. This then yields a second quite easy result for our electric field. E is equal to 1 over 4 pi epsilon naught times negative Q over r squared. At this point, we have finished 2 of the 4 calculations necessary to complete the entire problem. Let's move on to the tougher calculations, and in particular, let's deal with region 2 right away. Here we've reproduced the figure in a magnified view so that we can easily follow what's going on as we draw the Gaussian surface. We place the point P somewhere within the blue charge, the outer sphere, and we're going to do so at a radius r. When we ask ourselves the simple question, what other points have the same value of their electric field as the point P, we'll make a spherical surface as indicated by the dashed yellow lines. As always, our usual formulation of Gauss' law reduces to the simple form containing E times A. As with the other parts of the problem, the area will be the surface area of a perfect sphere. However, for this part of the problem, calculating the charge inside this Gaussian sphere is a little more complicated. Looking closely at the figure, we notice that Q in is going to come from the sum of two different terms. Let's call it Q red and Q blue. Q red is the portion of the sphere in the middle that we have contained within this Gaussian surface. Looking carefully at the figure and examining the yellow dashed Gaussian surface, actually we contain all of Q red, and so this term will simply be negative Q. It's clear that the charge we have taken from the blue region is a three-dimensional chunk of charge, and therefore the technique that we're going to use to get the answer is to take a charge density times a volume. As always, the charge density is going to be the total charge divided by the total volume. However, let's be careful. The blue sphere is hollow. If the blue sphere were solid, then its entire volume would be 4/3 pi c cubed. However, there is a hole inside the blue sphere. The size of the hole is 4/3 pi b cubed. Therefore, we can write down very quickly the answer for what is the total volume of the blue hollow sphere. This result has two terms, 4/3 pi c cubed for the entirety of the hollow sphere, and then you subtract away the hole to get the volume only of a spherical shell. Now that we've been able to write in a compact form the volume of a spherical shell whose outer radius is c and inner radius is b, when we look at the volume of the piece we have taken with our Gaussian surface, it is also a spherical shell, except that its outer radius is only r, not as big as c, but its inner radius is still b. After a very pretty cancellation, in which all of the 4/3 pi factors from every term in this expression drop out, we'll have a nice compact expression for Q blue, and that expression is Q blue is the total Q times the fraction r cubed minus b cubed over c cubed minus b cubed. Whenever you do a calculation that is this involved as we just did for Q blue, it's a good idea to go back and see if it makes sense by plugging in two extreme limits. Suppose the r, back in the figure, were equal to b. In this case, none of the blue charge would be contained, and our expression would have b cubed minus b cubed in the numerator. Boom! No charge inside. If, in addition to that, we consider what happens when r equals c, then we're going to find that we will have c cubed minus b cubed divided by c cubed minus b cubed for a factor of 1, so Q blue would be all the charge. These are exactly correct for the two limits on how much charge is contained by our Gaussian surface. Let's not forget that Qin is not Q blue. Qin is in fact Q blue plus Q red, and we can combine these to get the final result for Qin, which will then allow us to solve this part of the problem exactly. Here I've written the Q blue term first in order to make a pretty expression with respect to the minus sign. At this point, if you were to leave this as your expression for Qin, you still get full credit on an exam. However, since this is a review video, we're going to simplify by finding a common denominator of c cubed minus b cubed so that we get the following result for Qin in a pretty and compact form. Qin is Q times r cubed minus c cubed divided by c cubed minus b cubed. Let's check the limits one more time. At r equals b, this formula tells me I contain negative Q, and that's right, because that's the inner sphere. At r equals c, this formula tells me I contain zero charge, because that's what happens when you get all of the plus Q as well as all of the minus Q, and so this result for Qin looks robust, it passes the logic test, and we're ready to simply get the answer. Collecting all our terms together, we're then able to plug into the simplified Gauss law, where the integral has become simply EA, and then solve for the electric field, yielding the final result that E is equal to 1 over 4 pi epsilon naught Q over r squared, with the kind of crazy factor with the r cubed minus c cubed over c cubed minus b cubed. Rather than making this video particularly long by solving for region 4, we're instead going to simply recognize that region 4 is the same as the interior region in a previously solved problem on a solid sphere, and therefore we're going to reproduce that result here. yielding E is equal to 1 over 4 pi epsilon naught QR divided by A cubed. The final step, as always, in any Gauss law problem is to make a sketch of your result. To do that, let us collect together all 4 of these formulas and sort them in order of increasing R as we write them across the top of the page. When collected all together, our set of formulas are as shown in the table above. These have maintained the color coding from the previous calculations, and they are drawn in order of increasing radius from the R less than A formula all the way out to the R greater than C formula. For brevity, I've left out the E equals from each formula, letting that be implicit. One more alteration was made. In the previous calculation, while stealing the result from a previous problem, that problem had a positive charge for its sphere in the inside, and this problem has a negative one, and so this part of the solution has corrected that error by putting in a minus on front of the Q. Finally, let's finish out this problem. And the method by which we finish out any Gauss law problem is we draw a sketch, and the thing that we sketch is the electric field as a function of the radius. The tick marks along the R axis occur at 3 locations: R equals A, R equals B, and R equals C, and we need to follow each one of the formulas as they're given. Remember, when you look at the formulas, everything except R will be considered to be a constant while deciding what the shape of the line is, and so the first formula shows a negative constant times R. That's a straight line, except it slopes downwards. Following which, the next formula still has a negative, and it's a 1 over R squared formula. We often call that nyout, but in this case we're going to call that ny because it doesn't get all the way down to 0. Then comes region 2. We know that you enter at the purple curve. We know that you exit at 0 in order to match up with the green result. With a formula this complicated, I will not require students to have a definite shape for their curve. Just get there somehow, recognizing that the 2 endpoints of E equals 0 and E equals the result of that calculation must be fixed. Then finally, the electric field outside continues as 0 because every field line caused by a positive charge in our charge configuration has been captured on a negative charge because we have a total charge of 0. Finally, as you can see, there will be 2 tick marks that are necessary on the electric field axis, one aligned with the apex of the curve, and the other one aligned with the kink in the curve as R transitions across B. At the boundary, we can use either formula, and replacing 1 over 4 pi epsilon naught by K, we're going to have 2 results: negative KQ over A squared for the lower tick mark, and negative KQ over B squared for the upper tick mark. And that completes the Gauss law description of this very complicated charge distribution.